Hello students, this lecture is in the continuation of my previous lecture in which we have studied some basic concepts and results of the nth order homogeneous linear differential equation. Now in this lecture I will explain you some more results on the theory of nth order homogeneous linear differential equation. Starting with the fundamental sets, we will study the importance of fundamental set, and then with the help of the Wronskian of n functions, we will prove Abel Liouville formula. We will study the relation between the Wronskian and linear dependence and independence of solutions. I will also explain the proof of the theorem for the existence of a unique nth order homogeneous linear differential equation corresponding to any set of n functions f1, f2, fn with continuous nth derivative and non-zero Wronskian in the interval ab. And finally, we learn how to reduce the order of a given differential equation. And with the help of the solutions of reduced equation, we will learn how to obtain the solution of higher order equation. So let us start with the definition of fundamental set. A fundamental set is a set of n linearly independent solutions of the nth order homogeneous linear differential equation 1. That is, any set in which there are n functions which are solutions of the equation 1 and the functions are linearly independent, then that set is called fundamental set for the equation 1. For example, the functions exponential t, exponential t into t minus 1, 2 exponential t minus exponential 2t. These functions are linearly independent, and you can check that these functions are also solution of the third order homogeneous linear differential equation d cube x by dt cube minus 4 d square x by dt square plus 5 dx by dt minus 2x is equal to 0. For the solution, you have to put x is equal to et first, and then you have to prove that this satisfies the equation, third order equation, and then similarly for the second and third function, you have to substitute x is equal to exponential t minus 1 and x is equal to 2 exponential t minus e exponential 2t, and then you will get that substituting x for these functions, the equation gets satisfied, which implies that these functions are solution of the given differential equation. And for the linearly independence part, you have to prove that the Wronskian of these functions is never 0 for any interval ab. So in the like manner, I have solved one exercise for you in which I have proved that the functions t, t square, t cube form a fundamental set of the equation t cube x by dt cube minus 3t square d square x by dt square plus 6t dx by dt minus 6x is equal to 0 on every closed interval ab not containing 0. So you can see that if you name these functions t square, t cube as f1t, f2t, f3t respectively, then f1t satisfies the equation star. That is, when you substitute x is equal to t in star, then the equation star is satisfied. This implies that f1t is a f1t is a solution of the given equation star. Similarly, you can show for f2t and f3t. After that, this t square, t cube become a fundamental set if they are linearly independent. That is, if Wronskian of f1, f2, f3 is never 0 on the interval AB not containing 0. So when you check, Wronskian of f1, f2, f3 comes out to be 2t cube, and which is never 0 on any interval not containing 0. So both the conditions, that is t square t cube, are solutions of the equation star, and the set t square t cube is a linearly independent set of functions. Both the conditions implies that the set t square t cube is a fundamental set for the equation star. Now I will give you the existence theorem for the fundamental set. In existence theorem, we prove that there always exists a fundamental set of solutions of the nth order linear differential equation of type 1. That is, any equation of type 1 with coefficients as continuous function on the interval AB. So, the statement of the theorem is as follows. There exist fundamental sets of solutions of the nth order homogeneous linear differential equation 1 on the interval AB, where A is a continuous function on the given interval AB. That means कि आपको ये प्रूव करना है कि इक्वेशन 1 का हमेशा ही फंडामेंटल सेट ऑफ सॉल्यूशन एग्जिस्ट करता है. For that, we have already proved a similar kind of result for the system of equations, if you remember. And you know that an nth order homogeneous linear differential equation always corresponds to a system of n homogeneous equations. So, using the theorem number 5 for the system of homogeneous differential equations, we get that there always exists a fundamental set of the homogeneous linear differential system 2 on AB. So let phi 1, which is equal to f1, f1 dash up to f1 n minus 1, phi 2, which is equal to f2, f2 dash up to f2 n minus first order derivative, comma, phi n is equal to fn, fn dash, fn n minus 1th derivative, be such a set for the system 2. So this implies that phi 1, phi 2, phi n are linearly independent because it is a fundamental set for the system 2. Now we have proved in the converse part of the theorem 4 for the nth order differential equation that if phi 1, phi 2, phi n are linearly independent, then their first components, namely f1, f2, fn, also become linearly independent. Thus, f1, f2, fn becomes linearly independent. And also, the first component of these vectors phi 1, phi 2, phi n, that is f1, f2, fn, becomes the solution of the differential equation 1. So both the conditions, that is f1, f2, fn are solutions and f1, f2, fn are linearly independent, get satisfied. And this implies that there always exists a fundamental set of solutions of the nth order homogeneous linear differential equation 1. So this proves our existence theorem for the fundamental sets. And now, with the help of the fundamental set, we give representation of any general solution as a linear combination of solutions of one given in the fundamental set. That is, हमने ये प्रूव करना है कि कोई भी जनरल सॉल्यूशन दिया हो तो हम उस जनरल सॉल्यूशन को एज अ लीनियर कॉम्बिनेशन ऑफ फंडामेंटल सेट लिख सकते हैं. So let's start the theorem. Let f1, f2, fn be a fundamental set of solution of the nth order homogeneous differential equation 1, and let f be an arbitrary solution of above equation. So हमें क्या गिवन है? हमें n फंक्शंस गिवन है जो कि फंडामेंटल सेट बनाते हैं. वो फंक्शंस कौन से हैं? f1, f2, fn. एंड हमें एक आर्बिट्रेरी सॉल्यूशन दिया हुआ है जो कि हमें नहीं बोला हुआ कि फंडामेंटल सेट में है या नहीं है, हमें नहीं पता, बट वी नो दैट दिस f is an arbitrary solution. It is a solution of above equation. Then the theorem states that this f can be written as a suitable linear combination of f1, f2, fn. That is, कोई भी जनरल सॉल्यूशन है हम उसको f1, f2, fn के लीनियर कॉम्बिनेशन में लिख सकते हैं. सो कैसे? सो लेट्स स्टार्ट द प्रूफ. नाउ क्योंकि हमें पता है कि corresponding to any nth order homogeneous linear differential equation there corresponds a system of n differential equations. और उस n डिफरेंशियल इक्वेशंस के हम क्या करेंगे? सॉल्यूशंस मान के चलेंगे कि लेट phi1, phi2, phi n be the n solutions of the system of the homogeneous system 2 corresponding to the linear vector corresponding to the nth order differential equation 1, जो कि आपको f1, f2, fn सॉल्यूशन दिए हुए हैं तो उसके कॉरेस्पॉन्डिंग वी कैन कंस्ट्रक्ट द कॉरेस्पॉन्डिंग सॉल्यूशन ऑफ द सिस्टम. और उसको हम कैसे कंस्ट्रक्ट करते हैं? phi1, phi2, phi n की हेल्प से. और phi1 का जो फर्स्ट कंपोनेंट है वो हम f1 लिखते हैं और सेकंड कंपोनेंट f1 डैश एंड सो ऑन. हम चलते हैं f1 के n माइनस फर्स्ट ऑर्डर तक. सिमिलरली हम phi n तक लिखते हैं. एंड सिमिलरली क्योंकि हमें f सॉल्यूशन दिया हुआ है nth ऑर्डर डिफरेंशियल इक्वेशन का, सो वी कैन राइट f also, we can write solution phi corresponding to this f also, and the components of phi will be f, f dash and f n minus 1th order derivative tak. So let phi, phi1, phi n be the solutions of the corresponding system. Now, since f1, f2, fn is a fundamental set, ये आपको given है. So fundamental set है तो इसका मतलब कि f1, f2, fn क्या होंगे? Linearly independent होंगे. So we again use theorem number 4 on nth order differential equation, and उसके हेल्प से हम ये कह सकते हैं कि अगर f1, f2, fn लीनियरली इंडिपेंडेंट है तो phi1, phi2, phi n भी लीनियरली इंडिपेंडेंट होंगे. एंड दस phi1, phi2, phi n सॉल्यूशंस तो पहले ही थे. सो इट मीन्स कि phi1, phi2, phi n फंडामेंटल सेट बनाएंगे किसका? ऑफ सिस्टम 2 का. एंड यूजिंग थ्योरम 6 ऑन द system of equations, I'm saying this theorem 6 is on the system of equation. For the system of equations, we have already proved that any general solution phi for the system of equations can be written as a linear combination of the fundamental set. Therefore, जो हमने general solution phi लिया था उसको हम कैसे लिख सकते हैं? We can write phi as C1 phi1 plus C2 phi2 plus Cn phi n. That is, we can write phi as a combination of phi1, phi2, phi n. So अगर हम उसको phi को component wise लिखें तो phi के components हैं f, f dash up to f n minus first order derivative. एंड सिमिलरली अगर हम राइट हैंड साइड जो कॉम्बिनेशन लिखा है हमने C1 phi1 plus C2 phi2 plus Cn phi n उसको कंपोनेंट वाइज लिखें तो फर्स्ट कंपोनेंट क्या बनता है उसका? C1 f1 plus C2 f2 plus अप टू Cn fn. सिमिलरली सेकेंड कंपोनेंट बनेगा C1 f1 डैश plus C2 f2 डैश plus अप टू Cn Fn डैश, एंड जो लास्ट कंपोनेंट बनेगा वो बनेगा C1 Fn माइनस फर्स्ट डेरिवेटिव प्लस C2 Fn माइनस फर्स्ट डेरिवेटिव प्लस Cn Fn and minus first derivative. Now we can compare the corresponding elements in the two matrices. So we get, when we compare the first component, that F is equal to C1 F1 plus C2 F2 plus Cn Fn. That is, any general solution F of equation 1 can be written as a linear combination of F1 F2 Fn. So यही हमने प्रूव करना था. So this completes the proof of the theorem. So I have explained one example which uses above theorem, and in this example I have taken the function exponential t minus 1 comma 2 exponential t minus exponential 2t. Now you have already checked that this set of the this set of three functions becomes a fundamental set for the equation 1. Now because it is a solution, it is a fundamental set of solution, so we take another solution. Let ft is equal to 2et plus 3t plus 4e2t. Now we claim that this function is a solution of 1. It will become a solution of 1 if this ft satisfy the equation 3 cube x d cube x by dt cube minus 4 d square x by dt square plus 5 dx by dt minus 2x is equal to 0. So you can check that this function ft satisfy the equation 1. And after that we will prove that this function ft can be written as a linear combination of the fundamental set of functions. So if you make the combination as 13et plus 3et t minus 1 minus 8 2et minus e2t, then you can check this combination where I have taken C1 as 13, C2 as 3 and C3 as minus 8. Then ft becomes C1 F1 plus C2 F2 plus C3 F3. That is, ft can be written as a combination of these three functions, where F1 is exponential t, F2 is exponential t minus 1, and F3 is 2 exponential t minus exponential 2t. Now you have to check that these two functions, namely sine t cube and cos t cube, is a fundamental set of the differential equation t d square x by dt square minus 2 dx by dt plus 9t 5x is equal to 0 on every closed interval not containing 0. And now we will prove Abel Liouville formula for the nth order equation. Since you already know the Abel Liouville formula for the system of differential equations, so with the help of that theorem, we will derive the Abel Liouville formula for the nth order equations. So the theorem number 9 will give you Abel Liouville formula. So the theorem states, if f1, f2, fn are n solutions of the homogeneous linear differential equation 1 on any given interval ab, and t naught is any point in AB, then if W denotes the Wronskian of F1, F2, Fn, then Wronskian at any point t can be evaluated as Wronskian at point t naught into exponential minus integral t naught to t a1s over a naught s ds. Now let's start the proof. Since f1, f2, fn are functions of 1, so corresponding to these functions, we can write the solutions for the system of n equations. Let phi1, phi2, phi-n denote the solution for system of n equation corresponding to the nth order differential equation. Then the first component of phi1, phi2, phi-n will be F1, F2, Fn respectively. The second component of phi1, phi2, phi-n will be F1 dash, F2 dash, Fn dash respectively. And the nth component of the solution phi1, phi2, phi-n will be F1 n minus first derivative, F2 n minus first derivative, Fn n minus first derivative respectively. So now let W star denote the Wronskian of phi1, phi2, phi-n. Then using Abel Liouville formula for system of equations 2, we can write W star t is equal to W star t naught exponential integral from t naught to t trace as ds, where as is the coefficient matrix of the system 2. But Wronskian star t, W star t is same as W or W F1 F2 Fn, which is equal to Wt. That is Wronskian star, which is the Wronskian of phi1, phi2, phi-n. If you take the Wronskian of phi1, phi2, phi-n, then that is equal to determinant. In the first row, there is F1, F2, Fn. Second row, F1 dash, F2 dash, Fn dash. And in the nth row, F1 n minus 1, F2 n minus 1, Fn n minus 1. And that is same as कि अगर आप Wronskian लेते हो n functions का. Wronskian of n functions F1, F2, Fn is also given by the determinant, where first component in the row are F1, F2, Fn, second F1 dash, F2 dash, Fn dash, and in the nth row you have components F1 n minus 1, F2 n minus 1, Fn n minus 1. So W star t is same as Wt, and if you substitute Wt in place of W star t in 1, and you check that if you form the system, if you take the transpose trace, and if you check that trace of this matrix Ax for the system 2 becomes minus A1s over A0s. So substituting the value of Wt and trace As, we get so you can check that for system 2, trace of the matrix As becomes A1s over A0s with minus sign, and W star t, which denote the Wronskian of phi1, phi2, phi-n, is same as Wronskian of F1, F2, Fn. So if you substitute the values of W star t and trace As in the formula 1, you will get that Wt is equal to Wt naught exponential minus integral t naught to t a1s over a0s ds, which is the required Abel Liouville formula for the nth order equation. Now let's recall a result from the linear algebra, which I marked by theorem A. Now suppose m is greater than n, then a system of n homogeneous linear algebraic equation in m unknown always has a non-trivial solutions. That is, in an equation where the number of rows is less than number of unknowns, then the system always has non-trivial solution. So we will use this result in the proof of theorem number 10. So let's start the theorem 10. The statement is as follows. Suppose m is greater than n and let f1, f2, fm be a set of m solutions of the nth order homogeneous linear differential equation 1. Then we have to prove that f1, f2, fm are linearly dependent on the closed interval AB. For the proof, let any point t0 in the given interval AB, and we will consider a system of n homogeneous linear algebraic equations in m unknowns k1, k2, km so that we can use theorem number A. So the system we consider is as follows. K1 F1 T naught plus K2 F2 T naught plus Km Fm T naught is equal to 0. Second equation is K1 F1 dash T naught plus K2 F2 dash T naught plus up to so on plus Km Fm dash T naught is equal to 0. And the nth equation is K1 F1 n minus 1 derivative at T naught plus K2 F2 n minus 1 derivative at T naught plus K up to so on Km Fm n minus 1 derivative at T naught is equal to 0. So since you have given F1, F2, Fn, so you can always evaluate F1 T naught, F2 T naught and Fm T naught, and similarly their corresponding derivatives at the point T naught. So here the unknowns are K1, K2, Km, and this is a system of n equations in m unknowns. So using the result of theorem A, we can say that the system of equations 1 has a non-trivial solution. By a non-trivial solution, we mean that there exists C1, C2, Cm such that K1 is equal to C1, K2 is equal to C2, Km is equal to Cm, and where C1, C2, Cm are not all 0 because it is a non-trivial solution. So C1, C2, Cm should not all 0. And now, since we have to prove that F1, F2, Fm are linearly dependent, so we will consider a linear combination of these F1, F2, Fm with C1, C2, Cm. So let Ft is equal to C1 F1t plus C2 F2t plus Cm Fmt, and we name this equation by 2. Now, since linear combination of solutions is also a solution, therefore this Ft becomes a solution of the nth order homogeneous equation 1. And F at T naught is equal to C1 F1 T naught plus C2 F2 T naught plus up to so on Cm Fm T naught. And if you differentiate this equation 2 n minus 1 times and evaluate the derivative at t is equal to t naught, you will get n minus 1 equations as follows. First equation will be f dash t naught is equal to c1 f1 dash t naught plus c2 f2 dash t naught plus cm fm dash t naught. Similarly, if you differentiate second time, you will get f double dash t naught is equal to c1 f1 double dash t naught plus c2 f2 double dash t naught plus so on plus cm fm double dash t naught. And if you evaluate it, the equation 2 n minus 1 times and evaluate the derivative at t is equal to t naught, you will get the equation f n minus first derivative at t naught is equal to c1 f n minus first derivative at t naught plus c2 f2 n minus first derivative at t naught plus cm fm n minus first derivative at t naught. And you name these n equations. First equation f t naught, second f dash t naught, third f double dash t naught, and nth f n minus 1 derivative at t naught. This system of equations as 3. Now, if you compare the system of equations 1 and 3, from 1, you can see that the left hand side of 1, and from 3, you can see that the right hand side of 3. Left hand side of 1 and right hand side of 3 are same because K1 is equal to C1, K2 is equal to C2 and Km is equal to Cm. So equating these systems 1 and 3, we get that f at t naught is equal to f dash at t naught, which is same as f double dash at t naught, and f n minus 1 derivative at t naught, they all are 0 because in the right hand side of 1 it is a homogeneous system. So these terms f t naught, f dash t naught, f n minus 1 at t naught, they come out to be 0. Now from corollary of existence and uniqueness theorem for nth order linear equation, we have, if there is a solution ft and that ft satisfies that ft naught is equal to f dash t naught is equal to fn minus 1 derivative at t naught, they all are 0, then that ft is equal to 0. So using that corollary, we get that this ft, which we have proved that is a solution and satisfies the required initial condition as in corollary 1, we get ft is equal to 0 for all t in the given interval ab. Thus, from equation 2, we get that c1 f1t plus c2 f2t plus cn fnt is equal to 0. But c1, c2, cn are not all 0. So what does this imply? This implies that f1, f2, fn are linearly dependent because c1, c2, cm are not all 0, but f1, f2, fm is, but the combination c1, f1 plus c2, f2 plus cm, fm is 0. In our next theorem, we will prove that if the n functions f1, f2, fn are linearly dependent on the closed interval ab, and in addition to that, each of the function fi has continuous n minus first derivative on the closed interval ab, then Wronskian of these n functions is 0 for all t in AB. So this theorem gives us the condition relation, you can say relation between the linear dependence and the Wronskian of n functions. So let's start the proof. Since f1, f2, fn are linearly dependent on AB, so using the definition of linear dependence, there exists constant C1, C2, Cn, not all 0, such that the linear combination is 0. Now let T naught be any point in the given closed interval AB. Then C1 F1 T naught plus C2 F2 T naught plus Cn Fn T naught is equal to 0. Now differentiating this equation n minus 1 times, we get let us start the proof of the theorem. Now, since f1, f2, fn are linearly dependent on the closed interval AB, so it means there exist constant C1, C2, Cn, not all 0, such that C1 f1t plus C2 f2t plus up to so on plus Cn fnt is equal to 0 for all t in the closed interval AB, using the definition for the linear dependence of the n functions, and we name this equation as 1. Now let t naught be any point in the given interval AB. If we substitute this point in the equation 1, we get C1 F1 T naught plus C2 F2 T naught plus up to Cn Fn T naught is equal to 0. Now differentiate this equation 1 n minus 1 times and evaluate the derivative at the point t naught. We get c1 f1 dash t naught plus c2 f2 dash t naught plus on cn fn dash t naught is equal to 0. Similarly, when you differentiate it n minus 1th time and take the values at t is equal to t naught, we get the equation 1 takes the form c1 f1 n minus 1 derivative at t naught plus c2 f2 n minus 1 derivative at t naught plus cn fn n minus 1 derivative at t naught is equal to 0. and where C1, C2, Cn are not all 0. So it means that there is a homogeneous system of equations and equations, but C1, C2, Cn are not all 0. So it implies that the system of homogeneous equation has a non-trivial solution. So it means that the determinant of the coefficient matrix must be 0. So it means if you take the determinant of the matrix f1 t naught, f2 t naught, fn t naught, f1 dash t naught, f2 dash t naught, fn dash t naught, and f1 n minus 1 derivative t naught, f2 n minus 1 derivative t naught, fn n minus 1 derivative t naught, which is the coefficient matrix of the above system evaluated at t naught. So this determinant must be 0 because C1, C2, Cn are not all 0. And you can see that this determinant is Wronskian of f1, f2, fn at t0. Thus we get that Wronskian f1, f2, fn at t0 is equal to 0. Now since this t0 was arbitrary, and thus we get that Wronskian f1, f2, fn is 0 for all t in AB, which we wanted to prove. And thus in this theorem we proved that if f1, f2, fn are linearly dependent with some additional condition, then Wronskian is 0. But is the converse true? No, it is not true in general. That is, if we are given that Wronskian of f1, f2, fn at t is equal to 0 for all t, then this need not implies that f1, f2, fn are linearly dependent. So for that, we have proved one example in which I have taken the function f1t is equal to t cube, f2t is equal to 1, f3t is equal to mod t cube. And if you take the derivative of these three functions, you will get 3t square 0 and 3t into mod t respectively. And if you differentiate these functions second time, you will get 6t 0 and 6 mod t respectively. So clearly f1, f2, f3 has continuous second order derivative on each interval AB. And if you evaluate the Wronskian f1, f2, f3 at any point t, then it comes out to be 0. But you can check that f1, f2, f3 are not linearly dependent on any interval which includes 0. So let's start proving this. Let C1 f1t plus C2 f2t plus C3 f3t is equal to 0. And consider a small interval from minus epsilon to epsilon around 0. And now, in order to prove f1, f2, f3 are not linearly dependent, we have to find C1, C2, C3 and we will prove that the values of C1, C2, C3 comes out to be 0. So we make three equations in C1, C2, C3 because there are three unknowns. Now since 0 belongs to the interval minus epsilon to epsilon, therefore at t is equal to 0, if you evaluate C1 f1t plus C2 f2t plus C3 f3t is equal to 0, you will get C2 is equal to 0. And we name this C2 is equal to 0 value as 2, and the equation C1 f1t plus C2 f2t plus C3 f3t is equal to 0 as 1. Now take a point t1 in the interval 0 to epsilon, in the open interval 0 to epsilon. So then this equation 1 with the value C2 is equal to 0 becomes C1 T1 cube plus C3 T1 cube is equal to 0. And since this T1 is non-zero, so we get that C1 plus C3 is equal to 0 is the only possibility. And we name it the equation 3. Again, since T1 belongs to 0 to epsilon interval, so minus of t1 will belong to minus epsilon to 0 interval. And if you evaluate equation 1 at t is equal to minus t1, you will get that minus c1 plus c3 into t1 cube is equal to 0. And again, since t1 is not equal to 0, the only possibility is minus c1 plus c3 is equal to 0. And we name it 4. Now using 3 and 4, you will get that c1 is equal to c3 is equal to 0. And from 2 and 5, you get that c1, c2, c3 are all 0 in order to satisfy equation 1. So, f1, f2, f3 are not linearly dependent on any interval AB which contains 0. And thus, the converse part of the above theorem is not true in general when f1, f2, fn are given to be any functions and are not in particularly solutions of differential equation 1. And now we will prove that the converse of the above theorem is also true but under some additional conditions. So what are those conditions? So in theorem 12, we will prove the converse taking some additional conditions on the functions f1, f2, fn. So theorem is, let each of the functions f1, f2, fn have a continuous and minus first derivative with second condition that Wronskian of f1, f2, fn is equal to 0 for all t in AB. And if in addition to these two conditions, suppose the Wronskian of sum n minus 1 of the functions f1, f2, fn is unequal to 0 for all t in AB, then f1, f2, fn are linearly dependent on the closed interval AB. And so the additional condition is that Wronskian of sum of n minus 1 functions out of f1, f2, fn is unequal to 0 for all t in AB. So for the proof, let us suppose in particular that Wronskian of f1, f2, fn minus 1t is not equal to 0 for all t in AB. Then writing the equation Wronskian f1, f2, fn minus 1, x is equal to 0 in determinant form, we get that when we expand this determinant equation, then the equation is of order n minus 1 and the coefficient of the equations are continuous functions on AB. Why these are continuous? Because we have given that functions f1, f2, fn are all continuous up to order n minus 1. And because when you expand the determinant by the last column, then you get that the coefficient of the term xn minus 1, that is dn minus 1 x by dt n minus 1 is the Wronskian of f1, f2, fn minus 1 t. And this Wronskian is given to us as non-zero because we have assumed that the Wronskian of these n minus 1 functions is not 0. So the coefficient of x n minus 1 is non-zero and hence the order of this differential equation is n minus 1. And if you substitute x is equal to fit where I varies from 1 to n minus 1, in particular take I is equal to 1 suppose, then x will become f1t and x dash will become f1 dash t. X2 will be x double dash will become f1 double dash t and so on. X n minus 1 derivative will become f1 n minus first derivative. And if we substitute all these in the above determinant equation, we get that two columns, namely first and the last column, are identical, and hence the determinant becomes 0, and therefore the determinant equation gets satisfied for x is equal to f1t. And in a similar way, we can show that when you put I is equal to 2, then the two columns, namely second and last, are identical. If you put I is equal to 3, then third and the last column are identical, and so on. So all these functions f1, f2 up to fn minus 1 are solutions of this determinant equation, and therefore we have n minus 1 solution of this n minus first order determinant equation. But from the hypothesis, we have that Wronskian of f1, f2, fn is equal to 0 for all t in AB. This implies when you put fn in place of x, the equation is also get satisfied, and hence this fn is also a solution of this determinant equation. And thus f1, f2, fn are solutions of differential equation of order n minus 1, and hence we have set of n functions, namely f1, f2, fn, which are solutions to a differential equation of order n minus 1. So using theorem 10, we get f1, f2, fn are linearly dependent, and this completes the proof of the theorem. In our next theorem, we will prove that given any set of n functions, we can construct a differential equation of order n such that the functions f1, f2, fn becomes the fundamental set for the constructed differential equation. So the theorem states, let f1, f2, fn be a set of n functions, each of which has a continuous nth derivative on a given interval AB. And suppose the Wronskian of these n functions is non-zero on this given interval AB. Then there exists a normalized homogeneous linear differential equation of order n which has f1, f2, f3 up to fn as a fundamental set on the given interval AB. And this equation is given by Wronskian f1, f2, fn, x upon Wronskian f1, f2, fn is equal to 0, which I marked by number 1. So we want to prove that the equation 1 marked here is the required differential equation. That is, this is the equation of order n with f1, f2, fn as its fundamental set. So let's start the proof. First, we will write this differential equation 1 in the form of determinant and then expand it, the differential equation using the determinant. So writing the equation 1 in determinant form and expanding the determinant with the last column and dividing throughout by Wronskian f1, f2, fn, we get the equation 1 takes the form dnx by dtn plus p1t dn minus 1 x by dtn minus 1 plus up to so on plus pn minus 1t dx by dt plus pnt x is equal to 0. So equation 1 takes the form of this equation if we expand the determinant in the numerator by the last column and divide throughout by Wronskian f1, f2, fn t. Since f1, f2, fn are given to be continuous, we get pi's are all continuous on the given interval AB. And each of the functions f1, f2, fn is a solution of equation 1. Because if you substitute any of these fi's in place of x, you will get that there are two identical columns in the equation number 2 representing the equation 1 in the determinant form. So that determinant in the numerator, because of two identical rows, becomes 0, and thus our functions f1, f2, fn becomes the solution of this equation 2, and hence each fi is a solution of 2 and hence of 1. Now f1, f2, fn will become fundamental set if f1, f2, fn become linearly independent. Now since Wronskian of f1, f2, fn is not equal to 0 for all t in AB, thus using theorem 6 we get f1, f2, fn are linearly independent also. And this implies that this set f1, f2, fn form the fundamental set for the equation 1. And now we show that equation 1 is the only normalized equation with the required property. That is, this equation is unique one. There does not exist any other equation with having the same set f1, f2, fn as the fundamental set. So, on the contrary, let us suppose there are two such equations which satisfy all the theorem, and let the equations are marked by 3 and 4. Now subtracting the two, we get a homogeneous linear differential equation 5 of order at most n minus 1 having continuous coefficient, because when you subtract you get that the terms dnx by dtn are getting cancelled in both the equations, and thus you get the equation marked as 5, where the leading coefficient of the n minus 1th order term is q1t minus r1t. Now by the hypothesis, functions f1, f2, fn are solutions of 3 and 4, and this implies f1, f2, fn are also solution of 5, and which is an equation of order at most n minus 1. So here again we have n solution of an n minus first order differential equation. Thus this is possible only if each of the coefficient of the equation 5 is identically 0. That is, q1t minus r1t is equal to 0, q2t minus r2t is equal to 0, qnt minus rnt is equal to 0. Otherwise, if this doesn't happen, there exists some point t0 in AB such that qit0 minus rit0 is not equal to 0 for some I. And if this not equal to 0, then equation is of order less than equal to n minus 1, having f1, f2, fn as its solution, which is not possible as it contradicts theorem number 10. Thus, qit minus rit is equal to 0 for all I and for all t in AB. This implies that qit is equal to rit, and thus we get that the equation 3 and 4 are identical. That is, they are same, they are not different, and hence there exists only one and only one equation of the form 1 such that f1, f2, fn becomes the fundamental set for this equation 1. And now we will learn how to reduce the order of nth order differential equation. And with the help of this theorem, that is very important theorem and the last theorem of this section, we can solve the nth order differential equation with the help of the solution of n minus first order differential equation obtained by reducing the nth order differential equation. So the theorem states as follows. For a given non-trivial solution of the nth order linear differential equation, which I marked as 1, with the help of the transformation x is equal to ftv, we can reduce the equation 1 to an n minus first order homogeneous linear differential equation in the dependent variable w, where w is dv by dt. So let's see the proof. For the proof, we differentiate the transformation x is equal to ftv, and when we first differentiate it, we get dx by dt. And similarly, differentiating n times, we get d square x by dt square and dnx by dt n. And substitute these all x dx by dt, d square x by dt, dnx by dt n in the given equation 1. And when we substitute these values of x dx by dt, dnx by dt n in 1, the equation takes the following form. And now, rearranging the terms in decreasing order of the derivative, we get above equation can be written in the form of equation 2. Now, since f is a solution of 1, therefore, the coefficient of the term v in equation 2 becomes 0. Because you can see that the coefficient of v is nothing but when we substitute f in place of x in the equation 1, and f is given to be a solution of 1. Therefore, this coefficient must be 0, and thus we get an equation without the term v. And then taking w is equal to dv by dt in the equation 2, we can get the equation of order n minus 1. And we can write that equation of order n minus 1 in the form capital A naught t dn minus 1 w by dt n minus 1 plus capital A1 t dn minus 2 w over dt n minus 2 plus a capital A n minus 1 t w is equal to 0, and we mark this equation as 3, where a naught t is equal to where capital A naught t is equal to small a naught t into ft, capital A1 t is equal to n a naught t f dash t plus a1 t ft, and capital A n minus 1 t is n a naught t f n minus 1 t plus a n minus 1 t ft. And this completes the proof of the theorem, because now equation 3 is an equation of order n minus 1 with the dependent variable w, where w is given by dv by dt, and we obtain this equation 3 from the equation 1 by reducing the order of the equation n to n minus 1. And now there is a method to obtain the n solutions of the differential equation of order n from the solutions of the n minus first order differential equation. And the procedure is as follows. Now suppose we have reduced the nth order equation 1 to an n minus first order equation 3. And let W1, W2, Wn minus 1 is a known fundamental set of equation 3. Now, we define V1, V2, Vn minus 1 by V1 is equal to integral W1 t dt, V2 is equal to integral W2 t dt, and Vn minus 1 t as integral Wn minus 1 t dt. We have defined Vi's in this manner because we know that W is equal to dV by dt. So from here we can get that V is equal to integral W dt, and that is why we have defined Vi's in the above manner. Now, since W1, W2, Wn minus 1 are solutions of equation 3, therefore V1, V2, Vn minus 1 will become solution of equation 2. Together with these solution, taking V and t is equal to 1 for all t, we get that this V and t is also a solution of 2. You can check it easily. These and solutions, namely V1, V2, Vn of 2, are also linearly independent. Why these are linearly independent? Because Wronskian of V1, V2, Vn is not equal to 0. And thus V1, V2, Vn form a fundamental set of solutions of 2. But we want to find the solutions of equation 1. And for that, we use the substitution x is equal to ftv. In place of v, put the solution v1, v2, vn. So you will get n values of x. namely f1, f2, fn, which is equal to ft into vit. So from this you will get the n solutions f1, f2, fn of equation 1. When you substitute v is equal to vi for I is equal to 1 to n in the substitution x is equal to ftv. So this is the method how to obtain the n solution of an nth order linear differential equation from the reduced n minus first order homogeneous linear differential equation. So that's it, and I hope you understand the lecture. And based on the lecture, I have made an assignment for you, and the assignment contains only 4 questions. And with the second and fourth question, I have given you the hint to solve the problem. So try to solve all these questions, and you have to submit this assignment by Monday. So till then, take care and goodbye.